All right, guys, we're going to pick up where we left off before spring break with chapter 3. We were towards the end of chapter 3 and talking about Dirac notation. So just to review a little bit of that, in Dirac notation, we have something called the bra, right? We could throw an alpha in there, and then we have something called the ket. I could throw a beta in there. For some reason, we're missing the C when we describe those two things. So the ket is pretty easily a vector, right? We've already used that a little bit. The bra, on the other hand, is a linear function of vectors. So in other words, if we have something like an F in that bra, what we're really saying is that we have the complex conjugate of that F function, and it's going to be acting on something else. And the bra and the ket, of course, with our integral there, right? So we had already said that we can represent the state of our system by a vector, right? So let me give myself a second page here. We can represent the state of our system by a vector, and hopefully my handwriting is a little bit legible to you, if not completely legible. So we've got a vector that might be evolving with time, and we are hopefully in this Hilbert space so that we can use all these tricks that we've been talking about, right? And then our wave function is a coefficient of expansion of this vector on the basis of position eigenfunctions. So our wave function that has to do with position and time is going to be an expansion using those position eigenfunctions of this vector that's the state of our system, right? So if you were to write that x in this way as your vector, it's the eigenfunction of our unit vector with an eigenvalue of x. So here we're using x as kind of a placeholder for x, y, and z. That basis, if we're in one dimension, is just x, but if we're in more than one dimension, we'll have to use those others. And oftentimes you just use the letter E with a subscript 1, 2, 3. Okay, then we said our momentum space wave function that we also introduced when we were talking about our lovely uncertainty principle. Our momentum space wave function has to do with our momentum eigenvalues, and again, that state of our system that we can describe with this vector S. So you're expanding S on the basis of your position. You can also expand S on the basis of energy eigenfunctions. Which is pretty cool. So in discrete, let's be specific about that. In a discrete case, our energy eigenfunctions lead us to these n number of coefficients. And so those n's are given by our allowed energy. And so that n is the, is the nth eigenfunction. We'll fit it in here, of our Hamiltonian, right? So our functions that are given by psi, phi, given by psi, let's write all this down, given by phi, given by our collection of coefficients that is Cn, so that whole set, contain exactly the same information. And they are three ways to describe that same vector. All right, so we can use all three of these things. If you've got one, you can get to the other two, right? So one way we've said that is that if you've got one, like our wave function psi, we can do a transformation of that using this trick to get to our momentum space wave function that we called phi, right? So phi in our momentum space, that should just be a regular bracket there, parenthesis. We've got a square root of 2 pi and h bar on the bottom there, and then e to the I px over h bar, and this is over our momentum possibilities. And that also equals this from our allowed energies, all these stationary states. In a discrete case, we'd have the summation. So that's an E sub n times T over H bar. And then are just stationary states that have to do with position. Right? So operators representing observables are then linear transformations, and they can transform one vector into the next. So this should still be a review for you. So in that case, maybe we have an operator Q, so we'll use our generic operator, acting on a vector alpha, and that's going to give us this new vector beta. So operators representing observables are linear transformations that transform one vector into another. So if we represent our vectors with respect to a particular basis, so we're going to represent our vector, and remember my shorthand, with respect to a basis. So a particular basis, that's going to be some set of basis or some set of unit vectors that, like I said, we'll use E sub n by its components. That means that we are representing, say, our vector alpha as different components multiplied times those different unit vectors. So for a case that you know, if I gave you a random vector, you might describe it as 3 in the x hat direction plus 4 in the y hat direction plus 5 in the z hat direction, right? That is just a shorthand way of writing this, right? And this should be review from math and numerical techniques. Okay, so another way to write that is to say you're taking the inner product of your basis and your lovely little vector here, right? And then we can say the same thing for our beta vector up here, that our beta should be able to be written with our basis, right? And so each component of that beta vector is given by the inner product here. Those are two ways to write the same thing. All right, so in the same way, our operators are represented with respect to a particular basis by their matrix elements, right? So what I mean by that is our operators with respect to a particular basis can be written, and here we are going to give these different subscripts. So e to the m might be y and e to the n might be x or something like that. But they are just going to give us the different rows and columns of a matrix. So we will denote that by q sub m and then n. And we'll have a whole matrix that describes what this operator does to your vector to get a number out of it, right? So now, with that information at hand, we can say that this beta should equal q hat times our alpha. We're acting on our alpha, right? That was just our description from a couple pages ago. And that can be re-explained as our beta in terms of all the different basis and the coefficients in that basis should equal our q hat acting on our alpha. Well, we could describe our alpha as being these different components in our basis, and move the q hat in there, right? So if we take an inner product with respect to, or with e sub m, that equation to the right, I'm going to say that this is just a number, so it doesn't need to be in the inner product. So we've got em, en on this side. And then we're going to take an inner product over here. Again, a sub n is just a number. It's just our coefficient there for each of our basi. Sure. And we're going to have this going on. So in that case, the thing on the left, as long as we have a basis that's orthogonal and orthonormal, which we should, that is going to cancel out for everything except where m equals n. So in this case, we've just got bm. And on the right-hand side, what's in the brackets there is what I described up top here as describing our matrix elements. So we're going to have q, m, and n, and again, we're summing over n, times that number a n. So the matrix elements let you know how the components transform. So let's throw that in here, that little note. So these matrix elements let you know how the components of one vector transform into the components of the other vector, right? Okay, so when we have systems that admit only n states, let's go back to black. When we have systems that admit only n states, we would call that system a finite system, right? A finite number of states. Then we could say that this vector S of t that describes our system and that can be transformed or can be, transformed into our wave functions or our allowed energies and the coefficients associated with them. That vector is then in an n-dimensional state. So if that vector is in an n-dimensional, I shouldn't say state, I should say vector space. we can represent it as a column vector or a column matrix of n components. So you have what S1, S2, all the way down to n components, right? And that is all with respect to a basis. With respect to a basis, so each one of those components is with respect to E1, E2, all the way to E sub n of our basis. So if that's the case, operators, our Q operator, is then an n by n matrix. So we're going all the way out here, row 1, column n, and row n, column 1, right, all the way. So our operator is an n by n matrix. So here's where you guys having some ELA experience, either through our math and numericals technique course or actually through taking elementary linear algebra, makes understanding this section a little bit easier. So I asked you to do example 3.8 on your own and try to upload it to D2L. Example 3.8 is gonna try to help you look at doing that kind of math with and reviewing that elementary linear algebra math. Here you're just using a system where you've got two states, so you're going to have a 2 by 2 matrix that describes your system as a whole, or a 2 by 2 matrix that's going to be your operator. So the Hamiltonian is going to be a 2 by 2. And looking at how this actually applies to something here. So where did we even stop here? I guess that's about where we stopped. So then our Dirac notation after this section, we talk again about that bra and that ket in the book. And the operator acting on a vector just gives another vector, right? So with Dirac notation, if you've got an operator, I'll just be lazy and write it like this, acting on a vector, you're going to get another vector. So you're going to get another thing that is a certain n number column kind of thing. Your bra also gives you that instruction to integrate. You've got the ket, which is a column matrix, the corresponding bra. So the corresponding thing, let's say we have an alpha here, is going to be a row vector or a row matrix. So you would have A1, A2, and these are all complex conjugates up to whatever nth dimension you have for that row thing, whereas the ket is your column to do the matrix algebra correctly. If you've got a collection of all these bra things, these functions, that is another vector space, so you would call that the dual space. So the collection, what's that? Oh, collection of these bras is another vector space. And that other vector space we can call dual space. Right. So if we've got an alpha that's a normalized vector, you could have an operator we'll call it P, that picks out. So our operator P would pick out the portion of any other vector that lies along alpha, right? So if P then acts on some beta vector, what you're really saying is that you are going to put that beta in here in this inner product, and then do an inner product with alpha. And you're going to pick out that part of beta that lies along alpha. All right. And this one is supposed to be a triangular bracket and the other's not. So you might call that a projection operator, right? Because you're picking out the part of beta that is projected along alpha. Right, and that is the projection operator onto the one-dimensional subspace spanned by alpha. So if you've got some basis vectors that are discrete and orthonormal, your basis vectors that are discrete and orthonormal, so we've got a whole set of these basis vectors, right? So that's what we mean by this, a whole set of the basis vectors that we've said are discrete and orthonormal. Then let's throw, getting ahead of myself. Then those basis vectors, if they're discrete and orthonormal, are going to give us 0 when we take the inner product, except when they are the same thing. So except when m equals n, right? And then if we look at a projection operator that has to do with our basis vectors, and we sum them all up, we're going to get 1, right? So that's the identity operator. Not very exciting, but pretty useful. So if we let that operator act on any vector, we recover the expansion of that vector in the basis that we want. So that is just a very complex way to say this is how we get the components in that basis. So what that looks like mathematically is we let this projection vector operate on alpha. So just like we wrote before, we let it operate on our alpha. And we would write that in this way. Right. And that would give us this alpha within that basis. So our column matrix would be the components in that basis. Similarly, if we had a different set of these basis, if we had a different set, so we'll call it e to the z, that is Dirac orthonormalized and continuous. So these are our continuous spectra that we did this Dirac orthonormalization. So not a discrete basis, but a continuous basis. If we look at those guys, what we're really seeing, keep bumping things, making it hard to write. All right, what we're really seeing is that when we take the inner product of e sub z to e sub z prime, we're going to get this delta function, right? And that's from our Dirac orthonormalization. Then, because this is continuous, we're not going to have a sum, we're going to have an integral of these two things, right, our projection. And that should equal 1 when this is orthonormalized. Those expressions, this one with the integral and the one on the previous page, if I go back, with the summation, or rather this one, the identity operator. Those two things are the cleanest, the neatest way to express that idea of completeness that we talked about, that when we have something expressed in this way, it's complete, it expresses everything we need to express. When we write our bras and our kets in those, right, the things in those usually have a name for the vector in question, not just alpha or n. But we're working in a space of square integral functions, and we tend to name those things after the vector, rather, after the function that it represents. So if we want to do that, we can write the definition of a Hermitian operator in this way. Let's try writing legibly. So if we want to write the definition of a Hermitian operator with this bracket notation, with this Dirac notation, we might write it again like this, where we say that Hermitian operator can move to either side of these brackets, and it's going to be the same thing. So in Dirac notation, strictly speaking, that's not really how you would write it. You should really write the left-hand side with the operator separated in that way. On the right-hand side, how do you say this, right? This part of it doesn't make a whole lot of sense on that side. You could say really it's the name of whatever vector you're describing by this, right? Within that bra, which is a little bit strange. So we are kind of fudging around with the Dirac notation. And we know that that operator acts on the function of f and not just the thing that we call f, right? So an operator takes one vector in Hilbert space and gives you another, so it transforms it, right? We know that an operator could act on one vector and transform it, give you a new one, right? So what happens if we have the sum of two operators acting on a vector? Well, that actually works out in the way you would hope. So you've got the sum of two operators acting on a vector. You're going to have the sum of each operator acting on that vector, right? What about the product of two operators? So this one's the sum. What about the product? So the product of two operators, Q and R, acting on our vector? Well, all you'd really do is get whatever vector you get when R operates on it, and then let Q operate on that resultant vector. Right, so first apply that R hat to alpha, and then apply to Q to what you got. So order matters, right? Because you might get something different if you apply them in a different order. Occasionally, we're gonna experience functions as operators, and we'll see how that works as well. Go ahead and on your own, you can look at, so I'm gonna leave it to you guys because I know this is getting a little long. You wanna look at functions of operators at the end of this chapter. And then finally, you're gonna look at the section on changing bases in Dirac notation. So your experience with that would be like changing from a Cartesian basis to a spherical basis. You've already done this, but have you done it with this kind of notation? And you can look there at example 3.9 and 3.10 on changing the bases. We're just going from, say, the momentum operator, or from, yeah, our momentum operator to our position operator, or vice versa in that section. Right, so we'll end up there. I'll pick up with another lecture on chapter 4, and we'll just try to move along. I know these aren't the most ideal ways to take classes, so we'll see what we can do this semester. I'll talk to you guys again soon.